Hello everyone, this is the last lecture of this week. What we have been doing is we are exploring different methods to find out deflection in beams and frames, statically determinate beams and frames. What we will do today is, today we will see how the principle of virtual force can be used to find out deflection at any particular point in beams and frame. This method is also known as unit load method. If you remember, we have already discussed the method of virtual work and its application to determination for determination of deflection for truss. We have already discussed that. So, we are not going to discuss the principle of virtual once again here. We will just quickly review, spend one slide to quickly review what is the method, what are the different steps, and then see some examples. Okay. So, let us quickly review what is unit load method. Suppose we have a frame here. If you remember, we already obtained the bending moment and shear force diagram for this frame, and we have also seen the deflected shape for this frame in the last class. Okay. So, this is the deflected shape. So, point B comes to B dash and point C comes to C dash. So, let us see what is the deflection at point C. This delta AC comes to C dash. So, delta AC is the horizontal deflection at C and delta VC is the vertical displacement at C. So, suppose we want to find out what is the horizontal distance for at point C. Okay. Now, what are the different steps? The similar steps can be obtained for vertical displacement as well, or for that matter for displacement at any point. The first step is compute the bending moment due to the external forces. In this case, external force is vertical load P at point C, and if you remember, we already obtained the bending moment diagram for this beam, and this was the bending moment diagram. So, this is M. So, first we need to find out what is the bending moment at any section due to the external load. So, this is the first step and this is the bending moment diagram. Then what is the next step? Next step is apply unit load or moment in the direction of desired deflection or rotation. Means now take the same beam, same structure, same boundary condition. Now, at point C we want to find out the deflection. So, at point C apply unit load, and what would be the direction of this unit load? Direction of the unit load will be in the direction in which we want to determine the deflection. Now, if it is deflection, then a unit load needs to be applied, but if it is rotation, then unit moment has to be applied. Okay. Now, once we have this, then next is compute the bending moment due to the unit load. Now, this is the structure, same structure subjected to unit load at point C, horizontal load at C, compute the bending moment at any given location for this structure. Suppose this is small m, that bending moment is denoted by small m. So, what is the bending moment? For this, the bending moment diagram will be this. So, it is for segment BC, bending moment is 0, and for segment BL, it linearly varies. At point L, the bending moment is L, which is the length of AB. Now, so this is the bending moment for unit load. So, we have two bending moments, one is capital N, one is small m. This is for the externally applied load, and this is for the unit load applied in the direction in which we want to determine the deflection or rotation. Now, once we have this m and small m, and then the expression for horizontal displacement, at least for this problem, will be small m into capital M by EI. EI is the property of this, E is the Young's modulus, I is the second moment of area. And now, since in this frame we have two component, one is AB and BC. So, that integration has to be done actually on the entire structure, but that integration can be divided into several parts, means that integration can be done over each member and then sum them. So, this is very brief review of the unit load method. We have already discussed detail of this unit load method. Okay. Now, let us see some example. Before we do that, let us find out, let us continue with this example and find out what is the horizontal displacement for this. Okay. So, the problem was this. Okay. This is A, B and then C. So, this length is L, this length is A. So, and then delta AC will be, and then for unit load, this is the bending moment diagram for actual load is this is this value is PA, this is PA, this is also PA. Okay. And for unit load, this is the bending moment diagram, this distance is L, this is A, B, C. Okay. Now, what will be delta AC? Then delta AC will be first integration over AB, and that will be we know this is small m into capital M by EI into dx, integration over the entire structure. Okay. Now, this integration has to be done over AB and then BC and then sum them. So, AB means it is small m is this, the at any location, this distance is L minus x. Okay. Now, x varies from 0 to L. Okay. And then this is continued, this is constant PA. So, this becomes PA into L minus x, this divided by EI, this dx plus integration over BC. Now, BC, this part is 0. There is no bending moment due to the unit load on BC. So, this part becomes 0 into, and this part so this part anyway becomes 0. So, this part becomes 0. Okay. So, this is 0 to L and then integrate it PA L minus x EI dx, and this become P A L square by 2 EI. So, this is delta AC. So, this is the horizontal displacement at C. Now, if we have to find out vertical displacement, the same thing, this remains same, this capital M remains same. Only thing is, instead of applying unit load in horizontal, in this case the unit load was applied like this, and this is the actual load, this is P. In this case, unit load was applied because we wanted to find out horizontal displacement. Now, if we have to find out what is the vertical displacement, then unit load needs to be applied. Like this. Okay. And if we want to find out what is the rotation here, then instead of unit load, it will be unit moment. Okay. Now, if we get this value positive, means the deflection is in the direction of unit load. But if we get, you can apply unit load in this direction as well. I mean, if you want, you can apply unit load in this direction as well. But in that, if you do that, then instead of 1, it will be minus 1, and then this deflection you will get negative. So, negative means your deflection is in the opposite direction of the unit load. Similarly, for rotation, if you get the rotation is negative, then your rotation will be in the opposite direction of the applied moment. Things will be clear if we do some more example. Now, next example is a simply supported beam, which is subjected to uniformly distributed load, and we want to find out what is the delta max and theta A, means what is the rotation at A, and what will be delta max. Since it is symmetric, we know the delta max will be at the mid span. So, essentially in this problem, what we have to find out, what is the the rotation at A and what is the deflection, downward transverse deflection at the mid span. So, this is the problem. Okay. Now, we know that for this problem bending moment diagram is this, right. This is A, B, C, and the expression for bending moment we know that m, which is a function of x, is equal to q L by 2 x minus q x square by 2. We have done it many times, and at the middle at this point your bending moment will be W L square by 8. So, this is capital M, right. Now, we need to find out what is small m. Now, first let us find out small m for transverse deflection at C. So, what would be the problem? We need to consider same beam, same support condition at point C. Want to find out the vertical displacement. So, we need to apply an unit load at point C. This is A, this is B, and this is C. Okay. Now, we know that for this problem we know what will be the bending moment diagram. Bending moment diagram will be like this, right. We have already done it, A, B and C, and these values will be, the bending moment values will be this. That small m will be small m, it is unit load. So, it is half will be the reaction, half will be the reaction here. It will be x by 2, x is between 0 to L by 2, and m is x by 2 minus, or we can write L minus x by 2, the final expression, where x is between L by 2 to x to L. Okay. So, this equality also valid. So, this is the bending moment for the unit load. Okay. Now, what we need to do? We need to find out the vertical reaction. So, vertical reaction will be, we know that this will be delta, say V c will be integration of, we need to integrate over A c and then C b, though the expression for m is same for the entire part, but the expression for small m are different for A c and C b. So, this will be A c small m capital M by E I dx plus integration of C b small m capital M by E I dx, right. Now, write the expression for small m and capital M. Expression will be, this is x by 2 into, this will be q L by 2 minus q x square by 2 dx. You can take 1 by E I outside because it is constant, and this becomes 0 to L by 2 plus integration of L by 2 to L, and this become L minus x by 2, small m is L minus x, and capital M remains same. This is q L by 2 minus q x square by 2 and then dx. Okay. So, now if we do the integration, then this becomes, we will get 5 q L to the power 4 by 384 E I. If you remember, this is the value we obtained. We determined this deflection using direct integration method, using conjugate beam theory, using moment area method, and so you can verify these results with the results you obtain through other methods. Okay, this was for vertical displacement. Now, we need to find out rotation at theta, rotation at A. So, for vertical displacement we applied the unit load, but now for rotation we need to apply unit moment, right. So, let us do that. Take the same beam, A, B, midpoint C. Now, you apply unit rotation like this. Okay. Now, what would be the bending moment diagram for this? The bending moment diagram for this will be you check this is the bending moment diagram. And what would be the expression for bending moment diagram? Expression for bending moment diagram will be, expression for capital M will remain same because it is due to the actual load. Now, only thing is expression for small m will change, and the expression for small m will be, you check this, L minus x by L, and this is true for okay. Now, this is the expression for you can check when x is equal to 0, this become 1, when x is equal to L, this becomes 0. So, this is the expression for small m. Okay. Now, what will be theta A then? Theta A is integration of 0 to L small m capital M by E I into dx. Now, this becomes, let us say this become theta A is equal to, small m is L minus x by L, and then capital X, capital M is this q L by 2 x minus q x square by 2, q L by 2 x minus q x square by 2 dx, and this is 0 to L, this integration. And then theta A becomes, you can try this, W q L cube by 24 E I. So, this is theta A. Okay. Now, since delta C is positive, means it is the deflection is in the direction of applied unit load. Now, direction of applied unit load is downward, means your deflection is downward. Now, similarly, theta A is positive. If theta A is positive, then it means that your rotation at theta A is in the direction of applied unit moment. Now, this is the unit moment is applied in this direction. So, your rotation will be, and if we know that for the the deflection of the beam will be like this, and if the deflection is like this, then this will be theta A, this will be theta A, and as per our sign convention, this is positive. So, theta A is positive. Okay. So, that is how we can determine the deflection and rotation at any particular point. Let us do one more example. So, this is a frame. Now, again it has two member AB and BC. Member BC is subject to uniformly distributed load. Both the members are having same length, and see the support condition. This is hinge here, this is roller here. So, this is a statically determinate structure. What we need to find out? We need to find out what is theta A, means what is the rotation at point theta A. Okay. Now, so let us see this problem. The problem is this. Okay. Now, since we need to find out what we need to find out, we need to find out theta A. Now, first let us find out what is the bending moment for this. We have 2 points, one is AB and BC. For AB, M will be, you check that M is 0, and which is obvious because because if you take any point here, there will be no horizontal load here because this is roller support. Therefore, there is no horizontal reaction at A, only reaction will be vertical reaction. Let us draw that. If this is the if this is AY and this is AX and this is CY, AX will be 0 because there is no other horizontal load here, there is no horizontal constraint also. Now, CY will be QL by 2 and AY will be QL by 2. Okay. Now, if we take any section here, then at this section AX is equal to 0. If we take moment here, AY will not contribute because AY is passing through that point, AX is anyway 0. So, the moment will be 0. So, between A and B the moment is 0. Okay. Now, and what is the moment between for BC? For BC is, if we take any section, say if we take any section which is at a distance x, say measured from C, and draw the free body diagram of this. This is QL by 2, this is Q, and then this is Vx and this is Mx, and this distance is x. So, apply equilibrium condition, we get Mx is equal to, or M is equal to, since we are using M here, M will be is equal to QL by 2 x minus Q x square by 2. Please note, in this case x is measured from C, this point is C. Okay. X is measured from C. So, for real structure, for the actual load, this is the bending moment is 0 between A, B, and bending moment is expression is this between B and C. What we need to find out? We need to find out rotation at A. So, we need to apply a unit moment at A. So, let us apply that. So, this is the beam, this was the support condition, this is roller support, and then this is hinge support, this is A, B, C. We need to apply an unit, say this is the unit moment here. Okay. Now, you can, as I said, you can give the unit moment in other direction as well, then you, in that case you will get rotation is negative. Okay. Whatever value of rotation you get with sign, that tells you what would be the direction of that rotation. Okay. Now, let us find out what is the bending moment for this value, this length is L, this length is L, this length is L. Now, for this what would be the reaction? This will be CY, this will be CY, this will be AY, and this will be AX. AX is anyway 0 because there is no horizontal load, and then if you take moment about A, and then if you take moment about A, that is equal to 0. So, this is clockwise 1 and then anti-clockwise plus CY minus CY into L is equal to 0. This gives you CY is equal to 1 by L. Okay. CY is equal to 1 by L. Okay. Now, then the AY will be minus 1 by L because it has to satisfy equilibrium condition. Okay. Now, find out what is the moment for BC and what is the moment for AB. For AB, you take for AB, if you take any section here and AX will not contribute because AX is 0, A will not contribute because AY is passing through this section, only moment will contribute the moment at this section and the externally applied moment, unit load, unit moment here. So, what you get is, please check, small m is equal to 1 for AB. And similarly, for BC, what you get is m is equal to small m is equal to you take a section here, you take a section here at a distance x from C, draw the free body diagram of this section, and then we get m small m is equal to x by 1 by L is the Cy load into x. So, x by L. So, this is my and this is m for AB and this is m for BC. Now, then what would be the rotation? Rotation will be theta A is integration over AB small m capital M by EI dx plus again small m capital M by EI dx. Okay. And then small m is now for AB capital M is 0, small m is 1. So, for contribution from AB will be 0 and then only non-zero contribution will be from BC, where small capital M is this and small m is this. Okay. Now, if we so this becomes this contribution is 0. So, this become integration over BC and BC is means 0 to L, this length is 0 to L, m is x by L into capital M is QL by 2x minus qx square by 2 dx. Okay. Now, please if you do this integration, what you get is this is q L cube by 24 E I. So, this is theta A, this is theta A. Now, theta A is positive, it means that it will be your rotation will be in the direction of applied unit load. So, rotation will be like this. Okay. Now, just let us find out what could be the probable deflected shape for this structure. It is something like this, and this point is hinge, this point is roller. So, this point can move in this direction, and since this point is hinge, so and also we obtain that theta is positive, means the rotation will be in this direction, at least that is the applied unit load. So, it will be continuous like this and probably something like this. Okay. And this angle remain 90 degree because this joint is rigid joint. Okay. And this will sag because of this uniformly distributed load. This uniformly distributed load will cause sagging in this beam. But if you look at the similar problem, but when the load is concentrated load, this was the deflected shape. So, this is almost a straight line. Okay. It is not sagging like this. Okay. But in this case it will sag because it is supported here. This beam BC is supported at C and supported at B, and it is subjected to uniformly distributed. So, this could be the probable. I am saying probable because you need to find out actual deflected shape. Based on the information that what we have, we can say that could be the deflected shape of this structure, but that you have to verify. So, there are many examples, many problems like these can be we can find out what would be deflection and rotation at any particular point using method of virtual force or unit load method. It is just few examples I showed you here. If you take any book, there are many examples, many such examples for different kinds of beams with internal hinges, then different kinds of frames, different support conditions, again frame with internal hinges. Please go through those examples, go through those exercise problems, and then probably you can better appreciate the method. Okay. With this, thank you very much. Next week what we do is, next week we will start influence line diagram and moving loads. You see, as of now, whatever problem we have addressed so far, we assume that the load is acting at a point, and the load is also a static condition, it is fixed at a point, but in many practical cases load is not fixed, load is a moving load moves on the structure. Okay. Now, So, as the load moves on the structure, the internal forces, support reactions in the structure also continuously changes depending on the location of the load. So, we need to find out what could be the at a given location of the load, what is the internal forces and support reaction, or we need to find out what could be the critical location of the load where the internal force and support reactions are maximum. We will discuss all these things in the next class, influence line diagram and moving loads. Okay, thank you.